Okay, so my name's John O'Gorman. I'm currently based, well, I've been based here for quite a while now, but I'm west and south and west of Calgary, Alberta, Canada. So yeah, I really appreciate the opportunity to talk about some of the things I've been working on for a while now. So without further ado, always start off with my presentations with one or two quotes. I don't know if AEML knew that this was actually relevant to LLMs now, but when you think about things and you're asking LLMs questions about what you think might be important or what you think things might mean, it's quite different when you start getting thoughts out in the open. It's kind of the classic challenge, I think, with semantics and with all things kind of data and information and documentation. Thinking about it, writing about it. If any of you ever been in any kind of live theater, it's really easy to read your lines when you're on book, but when you start talking about them to and delivering them to other players, it's quite a different thing. So my contention is one of the takeaways if you're going to do anything valuable in information, you really have to be precise and diligently consistent at a granular level before you start creating or managing data. So this is kind of the thing that's come out of my 30-year experience in a lot of different areas of information management is that quality quality is everything. Quality ingredients, quality components, quality thought, quality structures. It's basically starting with the very small things. And when you take care of the small things, the bigger things tend to take care of themselves more or less. I firmly believe, and Eugene and I were talking about this earlier in the in the morning this morning, or in his case, very early in the morning. So yeah, it's a really important philosophy to keep in mind. So second thought, this is kind of a takeoff from Rudyard Kipling's "When Everybody's Losing Their Mind and You Can Keep Yours, You'll be a man, my son, or a real person sort of thing. So there's been a huge amount of hype around large language models and ChatGPT, and to be honest, it's really has sucked the air out of the room in a lot of different areas, mine included as an entrepreneur. It seems like that's what everybody really wants to talk about. But it's when everybody's kind of losing their minds about this stuff, it's a really good idea to step back and look around and see what's actually hasn't changed. And again, talking to Gene, what hasn't changed is the fact that people are still slowly getting used to the idea that maybe they should look upstream to find out where all these quality issues start from and where, for example, hallucinations in LLMs come from, and why ChatGPT is starting to the bloom is already off the rose and people are starting to realize they have work to do. They have to, in the vernacular of my to my kids, you have to eat your vegetables before you get dessert. Okay, bit about where I've been so far. I started out, believe it or not, like way back to the left of this particular diagram, doing something called Hollerith cards on mainframes. But I figured instead of making it really long back into the prehistory, I started out with this premise that I've come up with doing data analytics for a community university. They had their problem was that it was taking them far too long to get their reports out. And so I worked in the president's division doing data analytics at a very tender age of 34. And what was apparent from that exercise was that there was dimensions to these data in the university that were bound up in all these applications. So what we did there was we basically liquefied all of the data. And when we started putting it back together, we started to see some interesting patterns. Then I wound up in Silicon Valley working for a company called Documentum that was bought out by OpenText, which was bought out by somebody else. And the document management thing was interesting because they have this thing in document management called metadata. And the metadata is sort of like is equivalent to tags on how to describe documents. And it turns out the pattern kind of repeated itself because the dimensions of metadata were almost identical to the dimensions of the data analytics. Who wrote this document? When was it written? What is it about? Where is it relevant? That type of thing. All of those different language pieces were very similar to what we use for data analytic dimensions. Business analysis is where I make my bread and butter these days. And the knowledge graph that's come a long way in the last 5 or 10 years is now where I'm focused on delivering value. So that's kind of where I've been. And how these all connect, like nothing is a straight line. So every phase of my career, I find these things start to loop back on each other. So knowledge graphs and data analytics are related. Document management and metadata is related to dimensions that I mentioned. Business analysis, a lot of it is about process. But when you think about a process called, open a can of corn, it has task one, task two before you begin, task one, task two, task three, and then status values, all language values sort of mixed into, but like, how do you know you're done kind of thing. Knowledge graphs, as opposed to databases, give us much more freedom, much more degrees of freedom to describe and connect things. But knowledge graphs by themselves have the same challenge as application databases or ontologies or taxonomies. If you put two ontologists in a room, they're going to create 6 different ontologies for the same domain space, and none of them will talk to one another. It's kind of an overgeneralization, and I don't mean that in any disrespectful way. It's just that knowledge graphs and knowledge representation in general, I think, still has a challenge about identity, semantics, classification, connections, how edges are created. So that's kind of a little bit of my background. So the conclusion that we came to through all of those 30 years of experience is that language, especially now with the large language models, is the core of everything else that goes on with data and information. So we have the unstructured is content, semi-structured is things like forms, and there's a whole range of semi-structured information embedded in like CDs and videos, etc. And then the classic sort of structured, and I put unstructured in air quotes because language has a structure all its own, the syntax and grammar. But what we're trying to manage now is that since the boundaries are changing, we need to manage language at the beginning of our journey into data. So that's kind of one of the themes that we talk quite a bit about with our business. All right, so consider this. I was talking with Eugene about a fellow named Barry Smith, who's got some really, really, really excellent YouTube videos about how natural patterns of things, the small elements combine, and how upper level ontologies come into play. And the pattern seems to be that small numbers of elements combine in predictable ways. So for example, letters of the English alphabet, the elements in the periodic table, and everything up into like DNA and genes and those type of things. The point the Barry was trying to make, or he did make very actually elegantly, was, for example, in genomes, these patterns are domain independent. So the genomes that create a digestive system for a person are almost exactly the same genomes that create a digestive system for a cow or a beetle or a fish. So that's an important pattern to remember. And then upper level ontologies like BFO, Sumo, I don't have the well, BFO is like basic formal ontology, for example, and standard upper what's Sumo stand for? I should have gotten those because that's kind of one of the things I focus on. But they all have certain weaknesses, and again, I don't mean that in a pejorative sense, but there's always something missing. For example, BFO only likes to deal with, and most ontologies only deal with concepts. And in BFO's case, they only want to deal with what Barry describes as counting nouns, things that you can count, as opposed to what he calls mass nouns. And he uses packets of sugar as an example, which I didn't quite get, but they all have something slightly missing. So given that organizations spend literally hundreds of billions of dollars annually on these new shiny things that don't really work, then maybe it's time for a different approach. So we're talking about, you maybe have heard this phrase called shift left. So we're gonna, this morning and this evening and this afternoon, we're gonna shift way left. So in the case of ontologies, it means shifting up. So my contention is our theory is, and it's worked very well in a number of different verticals, is there is a way to organize upper level ontologies into a top level ontology. One of Barry Smith's question was, how do you know when to stop? How do you know where the top is? So hopefully this will give us give you the audience some idea where this is. Future-proofing classifications means, so we have to do two things in my view. Most ontologies deal with concepts. To create an RDF ontology, an RDF-based ontology, you use a subject, object, and predicate, or subject, predicate, and object. And typically the predicates are verbs and the subject and the object are nouns. and counting downs means that you can actually create sets. So that's one thing. We need to expand away from just concepts and verbs into things like adverbs, adjectives, those types of things, so we can make sense of anything that we're dealing with in a business, like status values. For example, when you talk about an active customer, what does that mean? The second part of that last statement is we need to reduce their complexity. So a lot of ontology creation, taxonomy creation is really difficult for laymen to implement or to understand first and then implement. So the proposal in front of you all this morning and this afternoon, this evening, and I'll just say today, because for sake of simplicity, is reducing the complexity. So we need to move the focus of poor data quality upstream to its origins in business language. The same principles apply to the food supply chain, manufacturing supply chains. The components have to be, if you're creating a space shuttle, the components have to be of the highest possible quality, and the same analog goes for food supply. Restaurants don't buy poor quality. If you delivered a half-rotten flat of tomatoes to your favorite restaurant, they chuck you out the door. We're starting to see this more, the shift left into, we need to manage these so-called vegetables and these very small pieces to get some really good quality downstream. So I'm going to talk a little bit more about, this is my view of the new supply chain. And I'm going to talk a little bit more about what these sort of boxes mean in a bit, but this is kind of where I see things heading. So from very highly granular on the left to highly structured on the right, BI cubes. The premise, and this is where Eugene and I got talking about a number of years ago, the premise is if you add semantics first and you add faceted classes, and I'll talk about that, what those mean in a minute, then everything downstream is structurally independent. So in other words, you can build knowledge graphs, you can build forms, you can build documents, you can build whatever the business needs without losing, and this is important, without losing the identity, class, or semantics of the components that you built it with. More importantly, and this is where, remember when I said I started at my career at the far right of this, doing analytics. The who, what, when, where, why, and how of analytics is exactly what we apply on the left, the far, far left. Okay, so having said all that, the must-haves for an upper-level ontology are top level. It has to be comprehensive. We talked about expanding beyond concepts and relationships. Technology agnostic, domain independent, and language neutral. So we don't want to be locked into a technology upstream or downstream for that matter. It's too expensive and it takes too much work. Domain independent means that you can take an existing structure or create a new structure for any domain. And I've used this model in 8 domains now, from manufacturing, education, healthcare, oil and gas. So you should be able to describe any future structure downstream, domain independent. Language neutral, equivalences is a huge part of this model, both in language translation for, say, English to German, for example, but also translating things like acronyms and abbreviations for new hires. If a new hire doesn't know what the abbreviation AFE means, or BOM, you should be able to deliver that equivalence in a very straightforward manner. Upstream top-level ontology has very, very minimal structure. There are no hierarchies, no subtypes, classes, or subsets. All of that stuff can be built downstream if you choose to, but an upper-level ontology must be structurally minimalist. And then expressive just means that you can, again, it's sort of related to the other 5. You can identify, classify, and describe context at any level below the top level. Okay. We need to manage things like same spelling, different meaning, different spelling, same meaning, persistence, equivalence, and association. And my contention is, rather than spend all this expensive compute time doing that on LLMs, we should be doing it upstream so you don't have to do it later. Why? Everybody in the room knows the problems about eliminating silos, improving findability. And the last one is really important too, is we're finding more and more applications like RAG and DAG and TAG and a whole bunch of AG things but the idea here is that anchoring LLMs in this approach really, really makes significant difference. How we talked about this a little bit earlier, we'll talk about this again. The identity class, explicit semantics, and consistent associations. And then the last one is when. And again, I can't stress this enough. Managing quality upstream upstream of the use in models and data and documents is when we need to do this. Okay, so this is what the upper level. These are the components of the upper level ontology looks like. It's based on Rudyard Kipling's 6 honest serving men, where his poem basically said, I have 6 honest serving men and can send them out anywhere in the world and they can they can come back with any of the answers. I call them who, what, when, where, why, and how. We've expanded those classes with a little bit more granularity to make it more explicit to say when we're talking about who, we're talking about organization or person, as opposed to, for example, the role is the why part of this is just more of a purpose kind of thing. It's not, it has much less to do with motivation than it has to do with purpose. So for example, disciplines are purposeful collections of language for, say, law, medicine, accounting, finance, et cetera, et cetera. Roles apply almost exclusively to persons and organizations. Use applies explicitly to human-made equipment and tools. For example, a pump or a drill has a use that actually is tied to a verb. So these 19 classes are all the classifications that are available upstream. The other thing to remember, and I touched on this briefly with the BI cubes, for example, is all these classes are mutually exclusive and exhaustive. They're called facets. So an organization facet has members that are not included anywhere else. And that part of the separation thing really serves you well when you're downstream doing analytics because it's already been set up upstream. The next one is expressions. Information and data, language is expressed in all kinds of different ways, abbreviations, acronyms, identifiers. So the number 42 can be a count. It can be an identifier. It can be a position. So we need to be able to have these expressions available to us when we're expressing things. The connectors, and again, this is a bit of a stretch for a lot of people that are working in the ontology, but this is the upper level connectors. You can add any other connector that you want to downstream, but on the upstream side, is they're meant to be read in both directions. So it seems a little bit grammatically like what the heck is he doing here? But equivalence, membership, precedent is really handy coming in for processes and procedures. Part has, so meronymy, where a lemon has, or sorry, seeds are part of a lemon, that kind of thing. And then property we added because the properties that we do use, and I'll show those in a second, people need to have the freedom to say that this object has this property outside of the property that are described here. So having said that, before you use any of these classification, expression, and connectors in a graph, for example, you have to declare a node. It's like knowing the meaning of a word before you use it in a sentence. So the final thing is every artifact, and we call them quants, but basically a meaningful token, if you will, has common properties. That has identity, class, expression, which you see there. It has a source, like where this came from. The scope is related to domain. So the scope could be something as broad as a domain. It could be something as narrow as a personal utterance, if you will. Contributor, we just keep track of emails about who actually contributed to the graph, status, and language that we talked about before. So it works because databases are structural representations, forms and templates are structural representations, documents are structural representations, sort of loosely structured, but it's still there. Knowledge graphs currently are collections of loosely associated facts. And again, my position is that they're loosely associated because you can create anything you want as A has something B. And then large language models are statistically generated associations of tokens, or collection of tokens. So we have all of these structural representation, but at the far left, at the top of all this, explicit semantics classification makes these all truly interoperable. So when companies tell you that they can do semantic operability by joining some tables together, they're basically just blowing smoke. Okay, so this is what this looks like on 3 levels. This is basically the architecture of this approach. We have a semantic core as a faceted glossary. Metadata level connects to actual structural entities. So column heading or a table name, for example, this works in greenfield and brownfield. Greenfield being like if you wanted to build something, or brownfield if you're trying to retrofit a graph, or this sort of approach. Instance data is faceted master and reference data. And then all of these together support business analytics and machine learning downstream. And you can do these, you can use LLMs to extract the semantic core, which we're doing now. You can use LLMs to extract metadata level values. You can use LLMs to extract instance data. The interesting part becomes in existing data, you need to be able to create equivalences of things that are either not spelled properly or that are translations of something else. So quick review. All data, structurally independent data, is created from the same stuff. That's one of our axioms, that there isn't any possible way to create data that's human understandable without using the language of the business. None of the structural representations carry explicit meaning. There isn't any way to get explicit meanings in a database table. I'm sorry, it just can't happen. Knowledge graphs are where that's happening. And I mentioned this before. The spend, I think, in the US alone on integration and cleaning data and data scientists is $21 billion US every year. And they're trying to fix this in all the wrong places. So upstream techniques are the best way to reduce costs. So this is a quick example of, we did a proof of concept with these ideas for a healthcare authority in Canada, in Calgary here actually. And we had 4 different systems. They're trying to knit them all together. So we applied these faceted classifications and the graph-based things. This is a doctor's clinical note. System 2 is a patient record. System 3 is a surgery schedule. And then this is the graph in the middle that we created from that. When you add these, when you identify what these colors all mean, so patient is a role, author Doyle is a person, male is a status, Bowen Rowe is a physical asset, Nanaimo, British Columbia is a place, et cetera, et cetera. And so the other part I want to point out here is that rather than just trying to join Arthur Doyle and this number down at the bottom, our approach creates a semantic equivalence between 900101 and Arthur Doyle. So now these 2 system records can be joined, and we can create a knowledge graph that has, in this upper right-hand corner are these, this is the patient's address, that's the address of the hospital where he's getting his surgery done. This is the patient address here. Same shape, different, same categories. These are the status values. This is the surgery. This is the event, for example. This is where the surgery is taking place. So with 6, using 6 of the facets, we're able to create a semantically equivalent structure, if you will, between an unstructured clinical note, heavily structured patient records that are quite different in their purpose, and then put it all in a faceted knowledge graph. Okay, so I'm just going to walk through this really quickly because I want to show you some of the other things that we're doing. So these are the 4 applications that we had to deal with. So the patient registry, the general practitioner's appointments, surgery schedule, and intervention detail. So the objective was to integrate all this data. And the question they wanted to ask was, how do wait times vary by age, gender, and the location of patients and the type of intervention? And it was a political question because what the government agency for healthcare here was constantly bombarded with was, it takes too long to get hip and knee operations. Let's do some analytics. So we took clinical notes. We took the GP appointments, the surgery schedule. This is a screenshot of our MVP. So this is the concept level, business concepts, metadata, and I showed you that sort of a donut shaped thing. So this is the concept model for this particular undertaking. This is the residence view. So residence is a use. It's basically a functional concept. Around the dotted lines, we're starting to get into more hypergraphs now. So street address is and again, when I say street address is a concept, I mean the words street address is a concept. As you can see that street address has a member 36 card crescent with the coordinates. But in the dark blue, these are metadata values that we've translated into human readable values that are concepts. And if anyone has any questions, I'm happy to answer that in a little more detail later on. But basically, this is kind of a three-level model. We have a residence concept. This is a hypergraph of an actual physical structure. It has a street address. It has a city, province, and postal code. And then these are the instances that we found in the databases underneath. So we found an address, coordinates 36 Car Crescent. It's in Alberta. It's in Medicine Hat. And there's relationships between these as well. This is the patient view, and this is actually from the larger. You can see where these edges go off into the space there. We'll show you the big picture in a second. Patient is a role, and again, the word patient is member of the role class, the role facet, because we have instances of patients that we want to have these things known about, and then we want to have these instance data. So M is a status, and it has an equivalent of male. 34870, that number there is a universal lifetime identifier. And then the birth date is 1947, November 18th. And then the patient is Adam Keller. So you can see these equivalents where these identifiers are used to connect patient to the schedule. This is the surgery view. So surgery is an event class member. I should be careful here because surgery is a surgery is an instance of the surgery event. These are all these are all the things we need to know about about a surgical event, any surgical event. This is what we found in the database area and in the clinical notes as instance data. So now we're getting down into the classes. These are the class views. So we have residence is still a use. We're leaving that alone. Street address, those are concepts again. So they're metadata, but they're also human readable concepts. P code stands for postal code. And then here we have the classification of these data values. Again, the patient role from the class facets, now we're getting into so instead of the business concepts, now we're getting into the classical view. So these are concepts. These are the things, these are the classes. So for example, male is a status. Adam Keller is a person. This refers to a person. The ULI, the universal lifetime identity is a concept, and that's the number, et cetera, et cetera. And there's a surgery event. Notice the colors are different. The shape is exactly the same as before, but now we can see, okay. I just put that right there. Okay. So yeah, so now you can just see the dimensions, if you will, the facets, if you will, of a given surgical event. And then the big picture, again, this is zooming back out. Business concepts in green, there's only 3 of them, metadata in dark blue, and instance data in. So you can see all of these are connected all in one place. Same thing, same shape. Now we're using a different key. So these are all the class facets. So we can slice and dice on these. We can take status of male and gender of male, and we can take residence, and we can take all of those things that they asked us to analyze. And then this is what we produced. So the faceted graphs, like the graphs we saw in the original sort of overview of the 3 systems that we're integrating, this is kind of how it winds up. And this is, I'm not embarrassed to say this, but I mean, this is as simple as importing the results into an Excel spreadsheet and creating graphs, like a graphic result. So this is the patient facet by gender. So we have male and female by location. And if you're doing a lot of BI, you recognize like, the sequence of that is count the number of people who have gender equals male or female and show me where they live. Simple. That's a who and a status and and then a location. These are surgical wait times so this is basically a span kind of analysis here. So you can see that the majority of this or the most common span between A surgeon saying, okay, we need to fix your knee or your hip, is right in this mark here. It's about 6 weeks. This is another intervention by gender. So we have the graphics. These come in really handy for saying, okay, I've got hips and I've got knees, I've got male and female, and I've got a little key to say which is which. Okay, so I'm going to switch gears here a little bit and show you that this is part of the, and I've got 10 past 12, so we're good for time, I think. Um, this is a $250 technology called the Brain. It's basically a mind mapping tool. And so we use this to demonstrate in addition to our MVP, which shows kind of the graphic approach. This is kind of a graph, but not a graph. It's more like like I say, a mind mapping tool that's got associative things. But just to orient you here a little bit, these are the 19 classes across the top. They're also represented as sort of a graphy kind of looking thing here. In order to get anything into this top level ontology, you first have to declare it. So we have the usual suspects like organization, we have persons, we have discipline codes. So this is the SAGD project is a steam assisted gravity drainage project in oil and gas. The objective, excuse me, the business objective of this one was they're trying to get their documents aligned because they were using several shared network drives. But in the process, they also wanted to identify key concepts, key people, key organizations, et cetera, et cetera. So you have the disciplines. So these are all the disciplines in this particular project, everything from accounting and exploration to health and safety and mineral land. And you've got places. So these are all places that might be associated with the project itself is in Algar Lake. This is where the project is located. But all of these ones, those locations could apply to, excuse me, could apply to location of suppliers, and we'll get into that in a minute. We also have roles. So we have roles that are outside roles, for example, manufacturers, suppliers, and vendors. These are all roles. And then we have everything from in here in this listing, excuse me, we have everything from consultants to contact shouldn't be a role. Anyway, geologist, office manager, VP engineering, etc. All these ones with the green are clickable, and I'll show you that in a minute. We have digital, excuse me, we have digital class functions, if you will. So for example, these would actually be otherwise defined as document types. So we have all of the document types laid out here. We also, for sake of convenience, engineers use a lot of acronyms. Part of the challenge they were having was every time they had a new hire, they didn't have an easy way to teach them acronyms except have them run down the hall and ask the production engineer, what does AC mean or what does CSA mean? So these all have all of these acronyms here, these initialisms, I guess is a correct term. They all have, they're all connected to CN is connected as equivalent to control narrative. I can sort of scroll down this list. I want to find out what FDN stands for. That's basically foundation. It goes all the way over here. Foundation piling, that's a discipline, a digital document type. Then we have we have use, and we have these organized by 3 categories. So this is status value, digital, logical, and physical. And we're going to go to physical. And you can also organize them by, if you have subcategories, these are concepts: building, equipment, instrument, and road. Those words are concept roads. We're going to expand the equipment a little bit. The equipment also as a category says a concept, but it also has these sort of subcategories of these functions, but they also have everything from aerial coolers. These are all of the equipment functions listed on the left. So let's go to one function called tank. And I've got this is kind of a cookies thing that comes in quite handy. So again, tank by itself is a function. In this case, tank is a functional word because it could be a concept word, but that's kind of the decision you make. And there's all of these different types of tanks. So this would be the diluent tank is a member of this class tank. I haven't put I can demonstrate that really quickly. Set type is a member. So this is this type of connection is a way of saying diluent tank is a type of tank. That's it. And a set-wise way of saying it is diluent tank is a member of the set tank. That's it. So we're gonna go sort of a little bit deeper into this and connect on pop tank. It's a member, and we can again assign it a set type is a member. But then we're going to go into this thing here. And this is an equipment tag. So this particular tag, and this is where things like tags and stuff can have tags of their own. So engineers are great for naming things. I just love the way they put these together. We don't all do that, but they do. But a newbie, a new hire might not know what 092 means. So he can go here and get the concept of 092, and I'll show that in a second. Tank, we've already seen. It's a tag. It's a member. These are all tags down this way. So you can see all of the tags that are used for equipment. But the thing I want to focus on now is this node here. So this being a tag, who supplied that tag? A company called GLM Industries, and it turns out they've supplied a whole bunch of tags. And if you look at where these tags come from, or where these tags are associated, or where they started, with something called a material requisition, which has the abbreviation MR up here. 100 refers to an area, 45 is a discipline, and AL1 is the name of the project. So you can see these very, very granular and expandable kind of things. For example, 45 is mechanical engineering. And these are all the documents that are relevant to mechanical engineering. So the facets here are actually acting as a navigation aid. You can do search up here. I won't do that today, but you can do search up here. But all of these pieces, all of these little strings, AL1, 143 EC, they're all described in the business glossary for this particular set of graphs, for example. But now I want to go from the other direction. So one of the cool things about facets is you can navigate from any direction that you want. So I'm going to go back to the beginning. I'm going to go to organization, GLM Industries. And here's all of the things that connect to GLM Industries. The fact that it has a vendor role means that these are all of the instances of vendor on the right. It's an organization. These are all of we talked about, these are all equipment tags. This is the material requisition. But what's important to them is this particular thing up here. This is the purchase order for this material requisition. This is where the money sits. So we've actually gone from all the way down down. So we've gone across all the facets to get to this GLM Industries. And then the question that we have is, who's my contact? And there's his phone number. So what you're actually looking at is kind of a flattened out cube of things where these 19 facets actually help the navigation sort of thing. So, okay, so go back to the presentation. The takeaways, semantic first, all types of data representations are made from the same stuff. A new level ontology must play nice with existing and new ontologies at every level. And finally, to arrive at semantic interoperability means that all form of language expressions must be included in a top level ontology. Sorry for reading those out loud, but those are the key 3 takeaways in this presentation. And I hope you've enjoyed it. And again, thanks so much for inviting me.